All right, so here is an Excel spreadsheet. I just made this one up, so I didn't duplicate exactly what's in the lab, but much of what you'll be doing in this lab will be replicating exactly the same procedures in order to compute the terms we just talked about, all the things like survivorship, lifetime reproductive value, generation time, that kind of thing. So let's get started. Let's go back to the age-structured population lab, lab 3, that's where we are, and start looking back at these terms. Oftentimes in a life table, you're given X, you're given K being the maximum age. So here K is equal to 20, and you're given the total survivors, essentially. This is the S sub 0 is the total number in the cohort. Oftentimes that's just conveniently set to 1,000. It certainly could be any number that we start at. We're basically following 1,000 individuals in this cohort all throughout their lifespan, all the way until the maximum age. This is the total number of survivors. Survivors after year 1, we had 750 survivors, 700 survivors at year 2, so on and so forth. And by definition, we have to have 0 survivors by the very maximum, by K. All right, so far so good. Now we have big S, the total survivors, sometimes called census size. And we're often not given D, but it's easy to compute big D. That's the number of individuals of age X who die before reaching age X plus 1. So let's actually make a new column here for D. So we'll call it D parenthesis X. And this is the total number of individuals that died before reaching age 1. So if we know that 750 individuals reached age 1, then we know that the difference between 1,000 and 750 is the total number that died. So there were 250 that died. And we can just kind of drag this down. 50 died from year 1 to 2, and so on and so forth. And we can drag this down and relatively easily and painlessly get big D, the total number of deaths at each age. All right, 50 deaths age 1, 50 deaths here. And you can see the death rate may kind of increase. There might be a kind of senescence process in this population, whereas old individuals start to have a higher risk of mortality. All right, so now we have death rate. Birth rate's often given to you in the life table, so as it is here. So we have birth rate, per capita birth rate. You see that there's a few years before the individuals in the cohort start producing offspring. So they start producing at around age 7 and kind of reach maximum reproductive fitness at around age 11, 12, 13, and then start dropping off. In the last few years of life, they're not able to reproduce at all through probably a senescence type process. All right, so that's the per capita birth rate. So that's given to us. And now we can start thinking about the derived terms. The first and maybe most important of which is survivorship. All right, L sub X, survivorship, is computed as the total number of individuals alive at age X divided by the original size of the cohort, S sub 0. So let's implement that. We'll call this L parenthesis X. That should be L parenthesis X, like that. And by definition, survivorship is 1 at age 0 because you haven't had time to die yet. Because this is basically at the time of birth, there's no time yet for any of the cohort to have died. So survivorship is 1 here. Now, for age 1, we can compute survivorship relatively easily, just as equal to 750, which is the number that survived to age 1, divided by the original size of the cohort. All right. Now that works for this computation. We have survivorship of 0.75 there, but if we drag this down, it's actually not going to work properly. Because what I need to do for the next next age is to divide the total number of survivors at age 2 divided by the original size of the cohort. B2, not B3. How do I make sure that this reference always stays fixed? Well, we remember what we did before. We just add a $sign to fix that reference. So now we can then drag this down the rest of the way. So that's survivorship. Hopefully that made some sense. Remember the fixed reference trick. So every time now we're computing the total number of individuals that survived to age 7 divided by the original size of the cohort, 1,000. And then here's the individuals that survive to age 9 divided by the original size of the cohort, so on and so forth. So that should be relatively straightforward. If you wanted to, and this is a concept really from the lecture page on age-structured populations, but it also comes up in this lab, so it's useful to go over it. The concept is survivorship curves. There are 3 types of survivorship curves: type 1, type 2, and type 3. Type 1 is like humans, where we kind of have high survival rates all the way until we reach very old age. So survival rate basically stays high and then dips at very old age. The type 2 survivorship curve basically represents kind of constant rate of survival across the entire lifespan of the species. And a type 3 survivorship curve represents high mortality at first for the very young individuals, and then much lower mortality or higher survival for older individuals. So there's 3 different types of survivorship curves, and the way to look at that is to take the log of the survivorship and plot that over age. So let's just do that really quickly, just so you get some practice working with survivorship curves. Taking the log of survivorship is easy. Might want to take the natural logarithm or log base 10. It does not matter. Either one is okay, right? So log 10, sorry, I'm not very good with Excel, as you can see. Log 10, if I want base 10, and I just put this reference in here, and I can just copy this all the way down. I don't want to copy it down here because log of 0 isn't a number, so I'm not going to do that. And if you want to make a survivorship curve, you can just plot. I'm going to use the control click here just to highlight only those 2 columns. I'm going to plot survivorship, log of survivorship. Survivorship curves have to be log survivorship over age, and then I'll just add a chart, and look at that. So there I have a survivorship curve, and that I will let you go to the lecture page and figure out what type of survivorship curve that is, but you might be able to guess right now. High survivorship all the way until old age, where survivorship drops off. That's a pretty classic example of, give you just a second, see if you can guess. It is, yes, a type 1 survivorship curve. All right, so that is, I'll just move that over because that's neither here nor there. Let's move back to the task at hand, working through all these life table parameters in Excel. All right, so we did survivorship. Survival rate is the next thing. So we want to get the rate of survival, the probability of survival from age X to age X plus 1. So to do that, there's a couple ways to do it. We'll call this G parenthesis X. There we go. And we compute that, so the survival rate of age 0 is the probability of surviving from 0 to 1. we can compute that by just taking the total number of survivors at age 1 divided by the total number starting at age 0, and that's 75%. Of course, that's going to be the same as the survivorship there, but now we can just literally drag down and get the survival rate. So we see that there's a 93% survival rate. That is 700 survived from age 1 to age 2. So that's a 93% survival rate, and so on and so forth. That should be fairly straightforward in terms of understanding and computing that value. So let's move on to something a little bit more complicated. The next thing is lifetime reproductive potential. All right. So lifetime reproductive potential is super important because it tells us if that's quantity R sub 0 is above 1, we know the population is above replacement level, that every female in the population should be able to replace herself with at least one female offspring. So that is really important. Let's compute it. We have to take our LX, which we've already computed, and take B sub X, which we've already computed. Or we didn't compute that, but we got that. That was given to us. And so we have these terms. Let's just compute this. We have to just take this product of L at age X and B at age X, and then add those products up across all the age classes, and that gives us the lifetime reproductive potential. So first, just to make life easier, let's make LX BX. I'll just call it LXBX. It's going to be the product of the survivorship and the birth rate. So that's going to be equal to the product of the survivorship times the birth rate. All right, so it's 0 there, and we can just keep dragging it down all the way down. All right, so that's LXBX, and to calculate the lifetime reproductive potential, we can put it anywhere we want. Let's just put it down here, lifetime reproductive potential R sub 0. And I'll make it bold because it's very important. And to calculate the sum across this range, we just say sum, and just drag this whole area, end parenthesis, hit enter, and we have R sub 0 of 2.73. So this population is well above replacement. If R sub 0 is above 1, females can replace themselves within the population, and we should have a stable or growing population, and this time we have a growing population. All right, so that's one really important parameter to compute, and that is one really important parameter down, but let's go through some more. All right, life expectancy. This is an important one as well. It's often something that one of the first things we want to know about a population. What is the life expectancy? We can approximate it by taking the total number of survivors, summing across all the ages, taking the total number of survivors and half the total number of mortalities in that time period or that age, that year of age, and dividing it by the original size of the cohort. And so that is relatively straightforward to do in Excel. So the first thing to do is to add up the total number of survivors and the total number of half the total number of deaths. We have the total number of survivors, we have the total number of deaths, and so we can start computing that. This is just an intermediate calculation we're going to need in order to compute the life expectancy. But let's call it S.5D. 0.5D. All right, that might be a terrible name, but that's what I just decided right now. All right, so you take the total number of survivors. So we had 750 survivors make it past age 0, and then we add 0.5 times the total number of mortalities at year 0. That is the number that didn't make it to the next time frame. We're going to give them each, say they lived each half a year. All right, so we had 875 here, and we can really just drag this down, because this now we say we had 700 survive that whole year from 1 to 2, and 50 die. We'll assume that each of those 50 lived half a year, and so on and so forth. So we can just drag this all the way down, all right? Basically until the very end. It's just going to be all zeros at the end. And to calculate the life expectancy at birth, life expectancy sub 0, I'll make that bold because it's also very important. Of course, everything we're talking about is very important. We take the sum of these, all the years lived by the entire cohort divided by the original number in the cohort. And we have a life expectancy of 8.676 in this population this made up population that I just made up like an hour ago. So this is life expectancy, and let's move on to, hopefully that made sense, generation time. Generation time is also something it's one of the first things we want to know when we're trying to understand how a species works, how populations work. Basically, it's kind of the way we think about it. It's like the time from birth to reproduction, and we're defining it here as the average age of the parents within a cohort. So we just monitor all the cohort throughout their entire lives, and we track when each birth happened. When each birth happens, we track the age of the mother, and then we do that, and we take the average of the age of all the mothers at the time they gave birth, and that is the generation time, and this is how we compute it. We take LXBX times the age and divide that by the sum of LX times BX. All right, so let's go back to Excel, and this time, instead of just having LXBX, we're going to make a column LXBXX. All right, so we're going to take the product of LX, survivorship, times the per capita birth rate at that age, times the actual age. All right, LXBXX, and we will go all the way down to the maximum age of 20, and that's LXBXX. So now generation time, big G, bold of course, is now equal to the sum of across all ages of LXBXX divided by the sum across all ages of LXBX. Sum of LXBX. Here we go. Generation time here is 11.32 years. That is just an estimate of the timing between birth and reproduction. All right, so that's generation time. We're moving, we're getting there. Intrinsic rate of growth. We can compute this really important quantity, intrinsic rate of growth, little r, which we've already seen several times. We can compute that as the natural log of the lifetime reproductive potential divided by the generation time. So we've gotten lifetime reproductive potential, we've gotten generation time, so this is really easy. Little r, that was autofill, that was not me. Okay, so little r is computed as the natural logarithm of the lifetime reproductive potential, in parenthesis, divided by the generation time. All right, 0.08894 is our estimate. Again, this is an estimate. It's not it's not as good an estimate as you get by applying the Euler method, but it's pretty good. So the little r is around 0.089. All right, that's easy. What's not easy? The next thing is reproductive value, or big V sub x. That's the future reproductive output of an individual of age X, the expected future reproductive output adjusted for the intrinsic rate of growth. All right, so let's implement this this equation here. This is the most complex of all the equations we're going to implement in this lab. So let's give it a shot here. So we first have to just compute. Let's just take this one by one. We'll compute this term e natural logarithm base e to the rx divided by L sub x. So let's compute that for every age. So we'll call it e to the rx divided by Lx. I know what that means. You might be able to come up with a better name here, but this is simply e, oops, I didn't put an equal sign, e to the r times x divided by Lx. All right. Now, this r shouldn't change. So this r term, I'm just going to put dollar signs to fix it. So it's fixed in place. I guess I really only need the dollar sign before the 29. It doesn't hurt to put it before the b, but it's not going to help. So now if we drag this down, we should get, oh, we don't need that last one. Divide by 0, not important. You can delete that. All right, so now we have the first part of this equation. Now let's see if we can tackle this whole term in one column in Excel. So let's see what we can do there. It's e natural, base of the natural logarithm to the minus ry, or this is just another way to get at age. This y refers to all ages greater than the age we're considering for the reproductive value. So e to the minus rx, or age, times the survivorship times the birth rate. Let's give it a try. So this is e to the minus rx. I don't know if minus they allow in names, but we'll try it. Lx bx. I believe that's right. Isn't that what we were? E to the minus rx Lx bx. Okay. All right. So equals exp negative 1 times minus r, and again, oops, I'll put that dollar sign there. So that's rx times that should be times x, right? And then times Lx times bx. Let's just make sure that's right. So we have e to the minus r times age times Lx bx. So that should be it. And then we can copy that down. All right. All right. Now, let's look back one more time. We have all the basic things we need, but for every reproductive value, it's going to be this term e to the rx divided by Lx times the sum from all ages greater than x all the way to the very oldest possible age class. We're going to sum up this product here. All right. That is a little bit tricky. Reproductive value for each age class. That was the right terminology, right? Oh, sorry, V. What am I doing? V sub X. V for reproductive value, not R, because we already have R down here. V, reproductive value, V. Okay, here we go. Here we go. Equals e to the Rx divided by Lx times the sum across all ages greater than the current age class of this term here, all the way to, I guess we can go all the way to 20. That means we should probably move this down. 20 really is the maximum, so we move this down. And this is divided by 0, so we obviously can't get a reproductive value for the very last age class. So I'll just put NA. It's not applicable. All right, so that's good. So we have the reproductive value for newborns. That's excellent. And if we want to get the reproductive value for the next age class, what we can do is just copy this down, but we keep that final we put a dollar sign at 22 so that it only calculates all the way to age 22. So if we drag this down, it should give us the reproductive value for the next. It's like this ERX divided by LX times the sum of all these terms all the way from the following age all the way to the final age. And so we can keep on dragging, and of course we can't compute for the very final year. I'll just delete that. But now we have reproductive values, and we see the final few years of life have no reproductive value at all because, look, there's no birth. Even if you survive, you can't give birth, so there's no reproductive value in these individuals. All right, any individual greater than age 15 essentially has no reproductive value in this population. What's the highest reproductive value? Well, looks like it's right here at age 9. So age 9 individuals have the greatest potential to produce offspring, and if you were to do translocation into a new population, you might translocate 9-year-olds potentially, but maybe it makes more sense to go with something like a 3-year-old, because keeping individuals in a captive breeding facility for 9 years is a lot of time. Anyway, lot to think about. This is not the easiest lab, so hopefully the demo made sense, and it'll make even more sense when you go through the simpler example that we go through in class or in the lab itself. So and please reach out to me or the TAs if you have questions. Good luck.